Okay, hi everyone. I think we have finally fixed the issue with the audio. It's a bit late now, but at least we managed. I think it's a problem is that certain microphones were connected, and now they have marked it, so I have to use the right one. I think this time it should work. In case you're interested in watching the recording, but in any case, for every recording, the one from Keller always worked in the other building, and the two classes are in sync. I know probably what you're interested most is the midterm. I can ask sort of general questions or answer the general questions related to the midterm. If you have certain concerns or questions, you're welcome to join or to come to the office hour tomorrow at I think 1:30, whatever it is that I wrote on the website. It's on the website on the office hour schedule, but it's 1:30 tomorrow. I would like to make then one or two very general comments about the midterm, but I'll wait until next week because there might still be a midterm or a makeup exam next week, and I don't want to give too much away to make it sort of fair across all of you. But next week I want to address at least one or two questions that I noticed made sort of caused the biggest troubles to my surprise, really. So I want to check these few questions with you next time. But at this point, last time we ended with formulating a dynamic program for comparing two strings, computing the so-called edit distance. We said this is the smallest number of edits we need to transform one input string into another using insertions of individual characters, insertions, deletions, and also substitutions of single characters. And so we started with considering two different cases of aligning the last two characters of a given prefix. So we thought considering the subproblem of two prefixes of the input strings might be a good idea. And so we sort of distinguished three different cases, how this last column in such a partial alignment might look like. The first case was, as you can see here, the first case simply aligns xi, the last character in our prefix of x, to a dash or to a, how did we call it last time? I think gap. Yeah, gap. Or we align vice versa, the last character of y to a gap symbol of x. And now the third case, this is where we stopped, is where we align xi to yj, meaning the last two characters of these two prefixes on top of each other. And therefore, my question for you is, what is the cost of the alignment which ends by aligning xi to yj? So based on what we have done last time, can you phrase the cost of an alignment that aligns xi to yj? So maybe just as a refresh here, in the previous case, in case one, where we aligned xi to a dash symbol, we had a cost of 1 for this particular alignment. We said whenever we insert or delete a character, we have to add a cost of 1 plus the cost of aligning the remaining string x1 through xi minus 1 to the entire string or the entire prefix of y to yj, y1 to yj. And the other case is symmetric. In the third case, my question to you, how would I formulate the cost of this alignment? Yeah. There might be a substitution, right? When you align xi to yj, it might be 0. There's one possible outcome. So the suggestion was that the cost is 0 once you align xi to yj. Can someone extend this idea? It's not entirely wrong. It's just not complete, let's say. Yeah. Yes, this is the contribution of the last column. Exactly. So if they're identical, then we don't have to pay anything. But if they're different, we have to pay a cost of 1 plus. So this is just the cost of aligning the last characters. But the entire alignment, how much does it cost? Why? Why 2? Oh, wait, yeah, no one. Some of all the changes which we don't know yet, right? So in terms of, I mean, if we know that we align xi to yj, we have a cost of 1 or 0, depending on equality of these characters, plus whatever it costs to align x1 through xi minus 1 and y1 to yj minus 1, right? Because this is what remains from these two strings once we align the last two characters. So here we have to make a distinction that if xi equal yj, then this contributes nothing, so there's no cost. Plus the cost of aligning x1 through xi minus 1. So not only, so we both prefixes will be shorter by 1 character, and y1 through yj minus 1. And we said if these two characters are not identical, xi is not equal yj, then we have a cost of 1 plus whatever it costs to align the remaining two prefixes. And in both cases, we're lucky because these two subproblems just correspond to pi minus 1, pj minus 1. So does everyone see that? So now, considering these three cases, if I want to compute Pij, what do I have to do? So the three possible outcomes, we want to find the best alignments, meaning the one with minimal cost. Let's say I try all these three. Which one do I pick? I can only pick one. Why? Why would I pick where xi and yj are aligned? That in that particular case, yes, it could be cost 0, but it might be that the alignment of the remaining prefixes is much more expensive if I cut off both last characters than doing what I do in the top, namely pij minus 1 or pi minus 1j. So these ones might be much cheaper. So I don't know. Yeah, we just try all three cases and take the cheapest. It's as simple as that. Let me write this down. But I mean, based on this comments, so you see that this is where it also differs from greedy. You said that we would pick the one where it doesn't cost anything because it seems to be locally the best decision to do. You take the one where xi is equal to yj, which doesn't cost you anything. But then it might be that sort of the subproblems are more expensive compared to the other choice. And that's why you have to run a dynamic program in this case. So in this case, what we would do is Pij is simply the minimum over these three cases. So like it is either 1 plus pi minus 1j, or it is 1 plus pij minus 1. So these are the first two cases. Or I'll say something about this in a second, diff ij plus pi minus 1 j minus 1. And this diff here denotes basically if they are, it's 0 if they're identical, and it's 1 if they are different. So this is what I tried to say with this diff. This is equal to 0 if xi equal yj, and 1 otherwise. So now we have all the ingredients actually for dynamic program. We have defined subproblems. We need to show that we have optimal substructure. And the final piece that is missing is sort of the relationship between these subproblems. So how do we create a solution to a subproblem from the solutions to smaller subproblems? And then we're essentially done. So for this, let us draw the subproblem graph that we introduced last time for this particular problem. So consider the following subproblem graph. So we want to, in the end, really solve this problem, Pm, n. So this means really we consider the prefixes of length m and n, which is equal to the input strings. So Pmn is what we're interested in. And by what we have just described by this recursive relationship between subproblems, is that this problem depends on 3 different subproblems, according to this maximization relationship, namely on Pm-1n and on Pmn-1 and on Pm-1n-1. This is how we introduce this subproblem graph, but with these edges that denote dependencies on these subproblems. And we can keep on doing this. Pm-1n will depend on Pm-2n. And Pm-1n will also depend on Pm-2n-2 and on this one. Similarly, I can draw. So I essentially draw these arrows always to the top, to the left, and diagonal to the one to the left and one up. So I can keep on doing this, which I won't do. But at the very end, we reach a point where we have P0n here's n-1, so P0 n-1. And we extend similarly to the left, all the way up to Pm0. And on the top left, we have P00. So this is the subproblem graph using this relation that we have just shown based on this maximization of the 3 previous subproblems. And our final goal is to compute Pmn, meaning the alignment of the entire strings of length m and n. And now you can see that we have all the ingredients for a dynamic program. The subproblems we said last time already have to be solved optimally. So in order to get the optimal solution for an alignment, we pick the last column, but we also have to pick the rest really optimally, the prefixes of the 2 strings. And the second ingredient we said for dynamic programming, remember what the second ingredient was besides optimal substructure? So when is dynamic programming really effective? Yeah. When the subproblems overlap. And why is this the case here? You can see in this subproblem graph, if you just look at Pm-1, n-1, it depends, or it's useful to compute 3 different problems. So whenever I want to compute Pmn, I need to look at Pmn-1, but also for m-1n and also for mn-1. So all these subproblems will go back to the same subproblem, Pm-1, n-1. So we'll recompute the subproblem multiple times. And that's true, of course, also for other subproblems. Yeah. Yeah, that doesn't seem right. It should be this should be m-2, n-1. Thank you. And so since we have all the ingredients for a dynamic program, we have optimal substructure, we have overlapping subproblems, we can try to build the optimal alignment now bottom up, starting from the smallest subproblem, and then reconstruct solutions to larger subproblems by using this maximality relationship that we just formulated. So let's write this down as the following function. So before I write this down, I mean, we have to make sure that whenever we're trying to solve a subproblem, that the subproblem this solution depends on have been computed previously. Right? So in our case for Mn, for example, we need to make sure that we have computed Mn-1, m-1, n-1, and m-1n. You can follow. So is there any order that you can suggest in which we can traverse these subproblems to make sure that all the subproblems have been computed before we reach our subproblem? So we start at the upper left corner, yeah? In which diagonal would you, so if you walk, so the suggestion was we start in the top left and then we walk diagonal down because we have this dependency to the upper left. Anyone agrees or disagrees? Who agrees that we can start on the top left and we just walk down on the diagonal? There's an agreement, one agreement. Who disagrees? One disagreement, two disagreements, okay. Okay, so we have a clear vote, 3-0. You disagree, and anyone can explain why he or she disagrees? You can change one variable at a time. You mean, so this variable you're referring to P? Ah, okay, okay. You can change only one at a time. Yeah, because so what goes wrong in this case, if you go diagonal, it would also depend on the one that is exactly up of you, right? So if you only had to in your scheme, you would have already computed only the one to the upper left, but not to the one to the top of it and to the left of it. And what you said, just to change one corresponds to essentially traversing this from, for example, top to bottom, row by row, from left to right. So if you just traverse this matrix from left to right, from top to bottom, then you will see that every time you compute such a subproblem, you have computed both the one to the left, the one in the previous row, and also to the sort of the left in the previous row. You can also do it column by column, so there's different ways to do it, but yeah, row by row is one way to do it. So let's write this down in the following procedure. So we call this edit distance of x and y. So like almost any dynamic program, we have to initialize sort of these boundary cases, the so-called base cases. These are basically the the 0 rows and the 0 columns. So these ones here, they don't depend on any other previous elements. And the cost, so what is the cost of, for example, 0, n minus 1? Anyone can tell me sort of the cost of these, the first row and then the first column? So if I take an element, for example, 0, n minus 1, what would be the cost of the optimal alignment? So 0, n minus 1 means that I'm aligning the first n minus 1 characters of one string to an empty string. N minus 1, exactly. It's n minus 1 because we can't align any of these characters to anything. So we basically align everything to a gap in this case. And that's why the cost of any of this is, in this case, n minus 1 or n, depending on which column you consider. And so for initialization, this is exactly what we do. We set all these pi zeros to i's. So we go over all i's from 0 to m and set pi 0 equal I. So this is true for the first column. And the first row, we go over all rows from j equals 0 to n and set p 0 j equal j. Okay, this is the initialization of the first row and the first column, and now comes the more interesting part. We again traverse, in this case, everything row by row. So we go from, again, for I equals 0 to m, and for every I, so for every row, we consider all columns from left to right. We go from j equal 0 to n. And we simply set Pij equal to what we have said before. We just take the minimum of the three values, namely the minimum of 1 plus p I minus 1 j and 1 plus p I j minus 1 and diff of ij, so 1 or 0, depending on if they're equal or not, plus the entry in the previous cell on the top left. And in the end, we simply return p mn. So the order of these two for loops doesn't matter, we said. If you do this column by column or row by row, doesn't matter, as long as we have pre-computed all three sub-problems. The running time, you have to fill this entire matrix, which will have size order m plus n, m times n. So this will overall have running time m times n. And it will, in the end, output the costs of the optimal alignment between the two strings, meaning the added distance. What we don't get using this alone is the actual alignment. In this case, we only get sort of the score PMN. We know that the added distance is 4, but we don't know yet exactly how to output the alignment of these two strings. So which columns we would align, which characters we would align to a gap. This is something we don't get from this. And we have to introduce some additional sort of tracking, where we always remember which predecessor we picked in this maximization here, in this. So whenever we pick, minimization. So we take the minimum element here, And every time we do this, we remember which one we picked, and then we will see in an example how you can sort of backtrack and reconstruct the alignments that led to this optimal score PMN that you're outputting. Okay, is any question before I come to an example? So let's go through an example. I think we had these two identical strings last time. And let's draw this subproblem graph and go through this example at least partially. So let's say we're having the following strings. We have A, C, G, T, A on the columns, and we have A, T, C, T, J in the rows. ATCTJ and ACGTA. Okay. So let's see. We started we initialized the first row and the first column. This should be easy. We have except that I made one mistake. I should move this one row down to have a 0 column. So the initial entry here will start. So 0, 0 is so aligning nothing to nothing will cost us nothing. Aligning nothing to the first character will cost us 1, 2, 3, 4, and 5. This is the initialization of the first row. The first column, we do the same. Aligning one character to nothing costs 1, 2, 3, 4, and 5. So this is this corresponds to these two first for loops where we simply initialize these boundary cases. And now if we start filling in the interesting cases, again, row by row, we start from left to right. And we consider this particular entry, this one here, I want to align A to A. So I can check the 3 different cases. I can come from the upper entry here and add a cost of 1, which gives us a cost of 2. I could also come from here and add a cost of 1, which also gives us a cost of 2. I could also come from here based on a cost of 0 and add another cost of 0 because A equal A. And so the cost of this will actually be 0. And as I said before, we keep track of which element we picked as the maximum, because this we will use later to reconstruct the actual alignments. And so I will mark this by this entry here. This red edge will tell me which maximum I picked in this case. So does everyone see how I picked that first element or the 0? I distinguished 3 different choices, going from the element on top, which has cost 1, and adding a cost of 1, which gives a cost of 2. The same from the left. And coming from the diagonal, I know that the previous entry was 0 plus an additional cost of 0 because A equal to A, and therefore the cost of this is 0. And therefore smaller than. So that's why I picked this one. And then I keep on moving to the right. So if I consider the next element here, I have again 3 different choices. Which one is the best? Any suggestion? Which one I would pick here? So what's the value I should put here in this entry here? One, yeah. And why? Because we could come from left and pay an additional cost of 1. So 0 plus 1 is 1. I could come from here, but then I would have to pay 2 plus 1, or I can come from here and then I would pay 1 plus, in this case, 1, because T is not, it's different from A, and that's why we would have to pay 2. So the cheapest option really is coming from left and paying this 1 additional cost of introducing a gap. So this is 1. So let's do this first row together. I don't know where the color changed now. What about the next entry? I forgot one thing, so I want to remember basically which one I picked. In this case, I came from the left. So what about the next entry? Can someone tell me what I have to fill in here? And why? You see the three different options that you have in this case? You can again come from the top, from the left, and from diagonal, and add a cost of 1 or 0. So which one is the cheapest? Yeah, so if you come from the left, again, you would have a total cost of 2. From the diagonal, you would have a cost of 2 plus, in this case, 1, because say C is different from A. Or you come from the top, but then you would have to pay 4 in total. So the coming from the left is the cheapest and costs you 2 units. And the next one, forgot again to keep track. Here is where we keep track. The 2 comes from here. And the next one, so what is the next entry? What do we have to fill in here? Yeah, 3. Yeah, why? Coming from where? The left, exactly. So we have a cost of 3, again, coming from the left. And the next one has a cost of 4, again, coming from the left. And we keep on filling out this matrix. I'll just write down everything without doing everything one by one. We will end up with the following entries. Just want to show you how we then in the end backtrack to reconstruct the actual alignment. So if I would keep on doing what we just did, you would end up with the following matrix. And you would have the following tracking errors here. So this is the result. What is the edit distance now between the 2 input strings? 3, exactly. So the cost, the edit distance is 3 because this is the entry of the lowest right entry in this matrix. So this is the P of MN, which is what we call the edit distance between these 2 strings, AC, GT, A and AT, CTG is equal to 3. And so let's try to reconstruct the alignment from this from these red errors. So how do we find the actual alignment that has cost 3? You will see that we actually have 2 choices here. So we start here in MPMN and keep on checking where we came from. So we know that we came from this diagonal here, and we again came from a diagonal, and then we can actually go 2 different ways. We can either proceed diagonally, or we walk up and continue then diagonal and left. So these are the 2 paths that basically reconstruct the alignment of cost 3. So let's try to do that. We start from the last column, and the interpretation is as follows. So if we have a diagonal edge, if we consider such an edge, we know that's the 2 corresponding characters in the 2 strings have been aligned. So match means really aligned. It doesn't mean that the 2 characters are necessarily identical. If I consider an edge to the top, then what it means is that I have proceeded in the first string, but I did not proceed in the second, so I have a blank in the top of the alignment. There's a black in the top of the alignment. Does everyone see that, diagonally speaking? So if you walk up, right, you see the interpretation, what it means if you go up from one entry to the one on top of it. So for example, if you go from here in this case, if you consider this edge here that we took, then what it means is that we have proceeded from this C to this G, but we stayed here in this C. So we proceed only in this one string, but not in the other, which means that we have aligned this G here to a dash, to a gap symbol in the other string. So let's try to write this down. And this is symmetric, of course, also for the other case. If you walk horizontally, then we have a blank. I think we call this gap. Let me replace this with gap. So if you walk horizontally, then we have a gap in the other one. Okay, so let's try this. So we start here, and we see that we came through this diagonal edge, this one here. So that means that I have aligned the G to an A here. This last character to this character, which is G to A. Let's write this down. I have aligned G to A. And I keep on doing this. I check this entry, and again, we came from the diagonal, which means I have aligned the respective two characters T and T. I'll write down T here and T here. And then we go to the next one, again, a diagonal path. So I know that I have aligned G and C. Let's write this. And then again, a diagonal. So essentially in this case, I really just align everything to everything and end up with this alignment. So this alignment I get when I follow this path here through my subproblem graph. So I mean, this what I'm showing here should be a straight diagonal. So in every step, I'm following sort of this diagonal edge, which means that I have aligned the respective two characters. And this is leading to this alignment. And the cost of this alignment, hopefully, will be 3. And so we have in this case a cost for the last column because they're not identical. We have a cost for this one, a cost of 1 for this one, and for this one. And the other two characters are identical. So the cost of this alignment will be indeed 3. So let's try the alternative path because, as I said, we have two choices here in this part. So what will you get if you would take the alternative route and start going up here? So the last two characters are identical because we follow the same two diagonal edges, meaning I'm aligning T to T and G to A as before. But then instead of continuing here with this diagonal edge, I move up. And now moving up really means that I proceed only in one string, but not in the other. In this case, it means that I'm aligning this G here, this G to a blank. So I will have gap blank to G. And after doing this, again, we follow a diagonal edge. So here, after moving up, we walk diagonal again, which means that I'm aligning the two C's in this case. So we write two C's here. And after doing this, I'm moving to the left. So now I have to introduce a gap symbol in the other string and align T to this one. And the last edge again in this example, again, is a diagonal edge, which corresponds to the alignment of A with A. Okay, this gives us a different alignment of the same strings. And you can see that the cost indeed is again the same, namely equal to 3, because we align here 2 mismatching characters. I have here an alignment to a dash, and if here another alignment to a dash, and the remaining characters are identical. So the cost of this alignment also is 3. So you can see the optimal alignment is not necessarily unique, but of course they have the same cost in this case, equal to 3. Now in a more general form, or is there any question about this? Did you see, does everyone see how I reconstructed the alignments from these red arrows? Yeah. The left, you mean this one? This is this one here. Because here you're aligning this T basically with a dash symbol, because you're moving left in this string, but you're not sort of making any progress in this one. You keep the A, and this is why this dash. So a dash in this case, if you go up, you introduce a dash in one string, and if you go to the left, you introduce the dash in the other string. So we moved once up here, which corresponds to this dash, and we moved once left, which corresponds to this dash. Any other question? So this is sort of the simplest form where every cost, or where every operation or every edit costs the same thing, namely 1 unit. This can be generalized to arbitrary weighting schemes where you have to pay, for example, a different cost for insertions compared to a deletion or compared to a certain mismatch. And if you do this, you obtain this more general form of alignments that was introduced, I think, first time in 1970 by Needleman and Wunsch. And later on, I think some 10 years ago later, it was extended to what's called local alignments, where you're sort of not penalizing misalignments in the beginning, at the end of the strings by Smith and Waterman. These are sort of 2 milestones really in dynamic programming. So just write down that they exist, but we're not going to go much into any detail. But the algorithm is exactly the same. If you have weights, you would have to do the exact same thing, and you would have the same dependency in this particular graph that we introduced. So if we weigh the gaps or mismatches according to some weighting scheme by different amounts. In this example, we all the weights were equal. We had a cost of 1 for everything. So just that you have heard of these algorithms, Smith-Waterman and Needleman and Wunsch. Sorry? Oh yeah, sorry, yeah. Good. If there's no more question, I wanna give you a different example for a dynamic program that has a slightly different structure. Maybe the one of computing optimal binary searches. So let's say you wanna translate a text in English into French, and you wanna create a dictionary for every English word that sort of leads you to the corresponding French translation. And you want to do this such that all your searches in this dictionary or the sum of these searches are minimized, such that you don't have to spend too much time overall translating this text. And you could do this with a simple balanced search tree that has potentially logarithmic depth. What this would not take into account is that certain words, again, maybe similar to Huffman encodings, might occur with different frequencies. And therefore, intuitively speaking, a word like the, which occurs probably very often in your text, should be somewhere high up in this search tree, such that you don't have to spend a lot of time every time you look up the translation for the. And a word like, and I took this from the book, a word like, I might also pronounce this wrongly, but it's called matriculation. A word like matriculation, which probably doesn't occur too often, can be somewhere deep down in this tree. Does anyone know what matriculation means? I had to look it up on Wikipedia. It's not a word that probably we use very often. It's this in old defense walls, when you have this opening floor through which you can throw hot water or boiling water or hot oil or something like this, or stones on your enemies, then this opening door is apparently called matriculation. And in most texts, I guess this word is not used very often. So this is the overall idea: organize these words such that the translation really becomes more efficient, in the sense that words that we look up very often are somewhere high up in the tree, and other words are sort of deeper down in this search tree. Call the optimal binary search. So the application that we mentioned is to translate English book to French. And you want to organize the dictionary for efficiency. So one thing to account for are words that don't have any immediate translation in French. So we have to take care of those too. And in the following example, we have only, let's say, 3 words that you want to organize in such a tree. 3 words, let's say the keys are K1. So we have 3 keys that you want to organize in a search tree, namely K1, K2, and K3. Sorry. I wanted to specify that K1 is smaller than K2, which is smaller than K3. Let's say in lexicographic order. And this would not be really useful. So what we also have to know is the frequencies with which these keys occur in our text that we want to translate. So we also know the frequencies or the probabilities of these keys occurring in our text to be P, Q, and R. So binary search tree, you know that we have the keys that are smaller than the root all to the left, and keys that are larger than the roots all to the right. So one possible way to organize these 3 keys are the following. We could have 3 as the roots. Then there's obviously nothing that is larger than 3, which you will indicate by this placeholder. So this indicates that there's nothing to the right. This is our largest word that we have. And so if there's a French word that would sort of be larger than 3, we would realize this by reaching this leaf. T2, I mean key 2. So when I write 2, I really mean K2. This could be the key that is right to the left of 3, and then I could just place 1 to the left of 2. And the remaining leaves are these, again indicated by these placeholders. These correspond to basically dead ends, where you realize that the word that you're looking for doesn't exist in your language. So this, for example, this indicator denotes that this would be any word that is somewhere between K2 and K3. So this would be And this, for example, would be words that are larger than K3. So what would the cost be in this particular example if I have organized these three words and they occur with frequencies P, Q, and R? The cost would be, and I'm assuming that the cost of looking up a single word is equal to the number of nodes that we have to check. So for example, if I look at word 1, I need to consider 3 nodes, namely the one for 3, and I walk to the left, I check the node for 2, and then I walk again to the left to find finally the node for 1. So the cost of looking up word 1 is equal to 3. So I have a cost of 3 times P. So P is the frequency with which this word 1 occurs. So I have 3P. Then word 2 has a cost of 2 and of course Q times. So we have plus 2 times Q plus 1 time R, because the lookup of 3 will just cost us 1 unit, and then of course 3 times. So this is one way to organize these words or these keys in a binary search tree. If we do this for, we can do this in a different way. We can also start and use 1 as our root node. Then to the left, there's again nothing. There's nothing smaller than 1. I could then proceed and use 3 as the root of the subtree. To the right of 1, again, there's nothing to the right of 3. And to the left of 3, in this case, would be 2, which is between 1 and 3. And again, to the left and to the right of 2, there's nothing. So this is a different way to organize, again, in a binary search tree, my words. And you can see that we preserve the same ordering of our keys. And in this case, the cost would be, I have a cost of 1 for word K1, which occurs with probability P. So I have a cost of P. I pay 3 for word 2, because there's 3 nodes on the path from 1 to 2. And of course, with probability Q. So I have 3 times Q. And R is the cost for key 3, which has cost 2. So I have plus 2 times R. So these are 2 possible binary search trees for the same set of keys with the same ordering. They will have a different cost, and the one that we finally want to pick depends on what P, Q, and R exactly are. So how often do these words occur? And accordingly, we would adjust sort of this organization such that more frequent words would be further up the tree. So one thing we cannot afford doing is try to simply enumerate all binary search trees of n nodes and just take the cheapest one. This is sort of the brute force way to do it. We can't do this because there's an exponential number of such trees. So really doing this would incur as an exponential cost. And therefore, we're trying to do something more clever and design a dynamic program to give us the optimal solution, meaning the optimal tree according to what I've shown here as the cost. So the cheapest tree for a given set of keys with an ordering. So say that we have now, instead of this particular example of 3 keys, let's say that we have n keys with certain probabilities, Pi. So say now that we have P1 through Pn, these are our probabilities of these n keys. And the keys, again, we denote by K1 through Kn in some order. And in addition, we introduce probabilities of missing keys between them. So for every one of these placeholders, I will have a probability that tells me with which I'm ending up in such a placeholder, and I denote this by Q. And so we have Q0, all Q1, all the way up to Qn. So these are probabilities of missing keys. Between our keys here. So Q0 is the probability of having something smaller than K1. Kn is the probability of having something larger than Kn. And Qi would be the probability of having something between Ki and Ki plus 1. So these are the probabilities for our placeholders. Yeah. But we have seen an example up there that we have two trees, right? And they both preserve the same order, right? So for every subtree, you have elements that are smaller to the left and elements that are larger to the right of the subtree, right? So this is true here, right? I started 3, and everything smaller than 3 is to the left, and everything larger than 3 is to the right. And this is true here too. I have 1 as the root, and I have everything larger to the right, and I have everything smaller to the left. So both of these binary search trees preserve this order, but clearly we have different trees. So in this model, all the P's and all the Q's basically describe all your event space. So if you sum up all the P's and all the Q's, they must sum up to 1. So this is a probability distribution. If I sum up all the probabilities of certain of our keys, so I go from 1 through n, pi, and I add all the probabilities of missing words in between. And here I have to go from 0 because I have Q0 also. Then this is equal to 1. And the problem is to find a binary tree that minimizes the following costs. This is the problem that we're interested in. Find a binary tree that minimizes the following costs. So in the cost function, we do essentially the same as we did here in the previous example of this of the 3 keys. We will check the depth of every element that we're looking for, and the depth is simply the number of edges. But I'm interested in the number of nodes that I have to consider once I'm traversing the path from the root to this element. So it's always the depth plus 1. This is the cost I have to pay for every element. And I have to do this as many times as it occurs in our text, which we model by these probabilities. So I have the probability of every element times the number of nodes I need to check every time I look up this one word. And I do this for all P's, and I also do this for all elements that occur in between our Q's to get the total cost of this tree. I need to sum over all our keys. I take the probability with which this key occurs times the cost of looking up that particular word, which we said is depth of I plus 1. And I do the same thing for our placeholders. So for all the keys in between. In this case, I have to go from 0, take the probability with which such a placeholder occurs, times the depth of the corresponding node. So depth of j plus 1. So again, this plus 1 is only there because we want to count the number of nodes and not the number of edges on this path from the root. And here actually I made a mistake here. To distinguish our keys from our placeholders, I'll refer this to the I will refer to the keys by ki, and I will refer to the placeholders simply by the index j. So when I say depth of j, then I really mean the depth of the node corresponding to the jth placeholder. But when I say depth of ki, this is really the depth of the node that corresponds to key ki. And this I can rewrite or simplify. Let's say I can take all these ones here to the left, this one, and the ones here to the right, and multiply them basically here with the corresponding probability, sum them all up, and obtain, yeah, what do I obtain then in this case? So what do I get when I take all these ones and these inner sums out and sum them up? So these ones, talking about these plus ones here, they occur in every single element in these sums. So if I take them out, I essentially just sum up all the P's and all the Q's, and they sum up to 1, as we know. So what you get is really 1 plus the rest. Let me just write it down, and then you can tell me if something is not clear. So this would be equal to 1 plus, and then the same as before. Sum I equal n pi depth of ki plus sum of all qj's. Does everyone see that? We just took out these ones within the brackets and summed up effectively all P's and all Q's to obtain this one single one here. Okay, so this is the problem. Is everyone is clear about the problem that we're trying to solve? To find the optimal binary search tree that minimizes the cost that I've just written here. And as we said before, the first ingredient we need for dynamic programming is optimal substructure. Why do we have optimal substructure and how? In this case, it's easy. Whenever you have a tree, this is very common that you essentially can just look at certain subtrees and that you can see that in order to compute the optimal tree, if you look at a subtree of the optimal tree, then every subtree has to be optimal with respect to the keys that are contained in the subtree. So every subtree will contain a certain range of keys, let's say from ki to kj, and you need to compute the optimal subtree that contains these keys ki through kj. Otherwise, you could again replace. This is this replacing argument, this cut and paste argument, where you could replace this subtree that is not optimal, containing elements ki through kj, by a one that is has a smaller cost, and then obtain a tree that has overall smaller cost. So this is a typical cut and paste. So every subtree of your binary, of your optimal binary search tree, has to be optimal again with respect to the keys that are contained in this subtree. So all subtrees of the optimal tree are optimal. Cut and paste. So this cut and paste argument we had already a couple of times. So now the question is, now we know that we have this optimal substructure with respect to smaller trees or subtrees. How do we construct a solution to our tree given the optimal subtrees? Right now we have to come up with sort of the relation between smaller subproblems and larger subproblems. So what is the subproblem that we are actually considering in this case? Well, a subtree in our optimal tree will contain a certain range of elements. And we consider a subproblem as the one where we try to find the optimal subtree that contains exactly this range of keys. We want to find the optimal subtree containing keys ki through kj. So this is a consecutive range of elements. Ki through kj with corresponding probabilities pi through pj. And we also have qi minus 1 qj. So these are all the probabilities we have. Again, the probabilities for the keys. These are these ones. So the p's are again the probabilities of our keys in the subtree, and these q's are the probabilities of anything in between these keys in the subtree. And we denote by Cij. The cost of, for searching sort of this optimal subtree. So the cost of searching this subtree. And how do we do that? So we have a certain range of elements from ki to kj. To come up with an optimal search tree for this range of elements, we have to first pick one of these elements as the root of our search tree. In the previous examples, we took two different choices. Once we picked element 3 as our root, and once we picked element 1 as our root. So we have to pick one root, one element in this range as our root, and then compute the optimal subtree to the left, containing all elements left of that root, or with keys that are smaller than the key in the root. And I have to compute the optimal subtree to the right of this root, which contains all the keys that are larger than the elements in our root. So assuming that j is greater or equal than I in this Cij. As I said, we need to select a root kr. This is one of our keys from within this range ki through kj. And make the following optimal. I'm just denoting this by a figure. So we have now in this visualization, or in this scheme, we have picked kr as our root, and then we have a subtree to the left, and we will have a subtree to the right of kr. And the left subtree of kr will contain all elements from ki all the way to kr minus 1. And in the right subtree, we have all elements from kr plus 1 to kj. So if we knew the optimal subtree, or if we knew which node is should be the root in our optimal subtree, we don't have to do anything. We really pick that as the root, and then recursively computes the optimal subtree from everything to the left and an optimal subtree for everything to the right of it. This is sort of the relation between subproblems. One thing to note here is that we have a special case where we consider the optimal cost of Ci I minus 1, so where the right index of C is 1 smaller than the left index. How can this happen? Well, it can happen if we, for example, pick the leftmost element as the root. So if I pick among Ki through Kj, Ki as my root, then I have nothing to the left. And so their left subtree would contain elements from Ki to r equal I, meaning to Kr minus 1. So this is basically what's written here. So if we look at these elements here in the left subtree, they always go from Ki to r minus 1. And then in this boundary case, r is equal to I. So I would have to consider Ci I minus 1 in this case. And the Ci I minus 1, does it make sense? It does make sense, because if you pick Ki as our root, I know I still have one element to the left, namely the placeholder that represents that we have picked something that is sort of smaller than Ki and doesn't exist in our dictionary. And therefore, we initialize these Ci's basically to, or these boundary cases, Ci I minus 1, simply as Q I minus 1. So this is sort of a subtree with one element that contains the placeholder, which occurs with probability Ki minus 1. And this is symmetric for the other case. So something similar would happen if I pick the rightmost element in this range as my root. Then again, I will have to pick to the right of it this one placeholder that is larger than Kj in our case. So what is the cost of the subtree now with these keys? How does it, how can we plug in the optimal subtree to the left in our overall subtree? So let's say you have computed the optimal subtree to the left and you plug it into your subtree that contains Kr as the root. What will happen to the cost of this subtree? Can you just, so what is the cost of that subtree with respect to the cost of the subtrees? So this one here, what's the cost of this one in relation to the cost of the two subtrees? Or in other words, what happens? So if I compute the optimal cost of this subtree, and I tell you what the cost is according to our definition of the costs, if I plug in this subtree into my overall tree, what will happen to the cost of that subtree? Will it remain the same? Will it increase? Will it decrease? Not clear? Is the question clear? Just want to see if you're listening. So if I compute the optimal costs of the left subtree that contains elements Ki through Kr minus 1, and I take this subtree and plug it into my tree that contains Kr as my root, what will this left subtree contribute to the overall cost of my tree? Plus, what was the last part? So it contributes whatever the cost of that subtree is, plus Kr. Yeah, the cost from going from Kr to the root of that subtree. Yeah, that's very close. So you said basically the cost of this one is the cost of this plus whatever the cost is from K. And what is the cost of this? It's exactly, yeah, 1, but 1 for every element in the tree, right? Because every element contributes, we have this somewhere here. So every element you can see contributes according to the depth of these elements. to the overall cost. And so once I plug in this left subtree in my overall tree, the depth of every element in the subtree will increase by 1. This is basically what you said with the cost going from KR to this. So the cost of every element in this subtree will increase by exactly 1. Sorry, no. The depth of every element in this subtree will increase by 1. And therefore the cost of this tree will simply increase by the sum over all P's and Q's that are contained in my subtree. I'm writing this down and then I'm gonna finish for today. So the costs of the subtree will increase by what we will denote by Wij, which is simply the sum of all the elements in this subtree. I'm going from 1 to j, and I add all the elements PL, plus going from 0, or sorry, from L equal I minus 1 to j, and I sum up all the Q's. Okay, any questions? If not, then I see you on Thursday. Thank you.